to the flat plane of the solar system. We know that Ison is a different kind of comet.
Its orbit reveals it has a unique path. Some comets orbit the sun time and time again. But Ison will swing by just once before heading outwards, never to return.
So to see where these comets come from, we have to step way, way back. We have to really take a big view of the solar system. Ison comes from much, much farther away, 10 to 100 to 1,000 times farther away, in a region that extends halfway to the next star. It's what we call the Oort cloud. It's a giant sphere of comets that extends halfway to the next star around the sun.
The Oort cloud is thought to contain up to 2 trillion icy comets. But where did comets like Ison come from? Astronomers like Amy Mainzer think the answer lies with the formation of the planets.
When the solar system first formed about 4.5 billion years ago, it started off as a cloud of gas and dust that collapsed to form a disk. And you can imagine, just like this sugar, all these little grains of dust circled throughout the solar system, spread in roughly a disk shape around the forming sun, which you might imagine to be here in the middle of the table. Now, eventually, under the influence of gravity, some of these little grains of dust are going to start to stick together, some of them starting to form little lumps, like these, right here. Now, some of the larger of these lumps are going to stick together to form the planets.
Most of these chunks smashed together, but some were flung outwards to form the Oort cloud.
And these can scatter really violently into the outer parts of the solar system, where they're going to stay in the deep freeze of outer space for billions of years in some cases. And one of these little chunks is Comet Ison.
It's an amazing revelation. Ison is a pristine piece of ice and rock left over from the formation of the solar system. And contained within this time capsule lie clues to how our planet evolved. Ison is speeding ever closer towards the sun, pulled in by its immense gravity. Astronomers have learnt it's left over from the formation of the planets. But what sent it tumbling in from the very edge of the solar system?
So if we take a step back from the Oort cloud surrounding our sun, we see that our solar system is just one star among hundreds of billions of stars that make up this giant collection that we call the Milky Way galaxy.
Galaxies aren't static. Over millions of years, they rotate.
If we speed up time and we look at this giant pinwheel we call the Milky Way galaxy, we realize that all the stars in it rotate around a common center, the same way that the planets in our solar system rotate around the sun. And every now and then, as this Milky Way galaxy is rotating, we pass by another star. And that star comes close enough to actually perturb the comets in our Oort cloud.
The extraordinary conclusion is the gravity of another star pushed Ison out of the Oort cloud.
Millions of years ago, close to the dawn of man, Ison was perturbed by a passing star and started falling in towards the inner solar system, towards the sun, so we could see it today.
It's an incredible thought. We're able to witness the final stage of Ison's inward journey. A journey that began when humans first walked the Earth. April 10th, 2013. Comet Ison is moving closer. It now lies within the orbit of Jupiter. It's close enough for Bonnie Meinke and the team at the Space Telescope Science Institute to capture detailed images using the Hubble Space Telescope orbiting above the Earth.
Hubble's designed to look at small things, distant things, faint things, and that's what Comet Ison is at this point. It's just a small hunk of ice out there in the far solar system.
These images of Ison reveal something intriguing.
What we're seeing with Hubble is that Comet Ison is developing a coma. And that's a huge layer, kind of like an atmosphere around the nucleus of the comet. It's full of gases, and they're raging like a snowstorm around this nucleus.
Ison is erupting clouds of gas in a process called sublimation.
I'm going to show you how that works with some dry ice and some water. So we have our dry ice in a bowl, our cryo gloves for safety. We can put those on, pick up a small piece of dry ice, and we'll place that in the water.
As the dry ice hits the warmer water, a chemical reaction occurs. The ice turns straight from a solid into carbon dioxide gas, causing it to fizz violently. Amazingly, Comet Ison is undergoing the same reaction.
This is exactly what happens with comets as they come into the inner solar system and warm up as they get closer to the sun. All of that solid ice begins to sublimate and form a coma.
As it continues to heat up, the dry ice fizzes even more.
So you can see that the chunk of ice is now beginning to spin. And that's because gas is coming off in different directions.
But what's exciting about Ison is just how much gas its icy nucleus is releasing.
Hubble is showing us that the whole coma is about the size of the United States. But if you move all that away, you can see that the nucleus is tiny, only about the size of Manhattan. That tells us that this comet is raging.
Even in the freezing depths of space, Ison is violently reacting to the heat of the sun. Most comets out here are usually inactive.
So if Comet Ison at this point is able to create such a huge coma out of a very tiny nucleus, this bodes well for its future. Hopefully it'll continue to get brighter and brighter.
We are able to see Ison because of sunlight reflected from gases and dust that make up its coma. But as it continues to warm up, something incredible happens. Its gases start to glow with a light of their own. This gives astronomers a unique opportunity to see what Ison is made of. It's similar to what we see with everyday street signs. Their tubes are filled with gases like neon. Electricity passing through the tube energizes the gas, causing it to glow brightly.
So here I have a lamp that is filled with gas that I'm going to make glow when I click the switch on. And it is emitting light, the same way that gases in a comet's coma emit light. And it looks to you like it's a reddish-orange glow.
In fact, the orange light emitted is made of a number of different colors mixed together.
When I hold this film up in front of it, you're going to see that light split into many, many, many different lines. Mostly red and orange, a little bit of green. The exciting, fascinating thing is that I can tell you that this must be neon atoms in that tube.
Every gas produces its own unique pattern of lines when it glows. These are called spectra. Like a barcode in a supermarket, if you can identify the spectra, you can identify which gases are glowing. And that's incredibly helpful when studying Ison.
So if I know what this is doing in the lab, and then I go and I look at a comet and I see these 4 lines, I know that there's neon in the comet. And seeing the glow of the atoms and the molecules in its coma, we can tell you what's there, and we can tell you how much is there.
It's a powerful technique called spectroscopy. And over the coming months, it will provide astronomers with a detailed breakdown of Ison's chemical composition. Spectroscopy has allowed scientists like Lewis Dartnell to build up a chemical profile of comets, and it's revealed some startling results.
What we've discovered more recently, there's a lot of other very intriguing chemistry, a lot of very exciting molecules that are mixed into their recipe alongside the ice.
ISON is a time capsule. Locked in it is the chemistry that existed when our solar system and Earth formed.
What really excites me personally about these comets is what they can teach us about the kind of primordial chemistry that would have been around in the early solar system. And ISON in particular is unique because it's falling into the inner solar system for the first time.
The chemical information scientists glean from ISON could provide answers to one of the greatest mysteries of our planet. Comets have long been mysterious objects. But as science historian Patricia Farah knows, their ghostly apparitions helped prove one of the most important scientific theories of all time. The evidence lies in a book over 300 years old at Clare College at the University of Cambridge in England.
This book is Isaac Newton's Principia, and it's the single most important book in the history of science. It's in this book that he describes gravity as a force that holds the universe together.
It's often said Newton hit upon his theory of gravity while watching an apple fall from a tree. But the truth is very different.
Towards the end of 1680, a new comet appeared in the sky, and many people were absolutely terrified. But for Newton, this was a new opportunity. It was a challenge to try and work out what was happening.
Newton was thinking how gravity might explain the elliptical orbits of the planets around the sun. But the movement of comets remained mysterious. Could they also be explained by gravity? Newton sets about measuring the 1680 comet as it slowly moves across the sky until it's lost in the glare of the sun.
He's showing the time the comet appears, where it is with respect to the sun, the longitude and the latitude of the comet.
What he sees next intrigues him more.
Then, a few months later, beginning of 1681, there's another comet in the sky, so Newton tracks that, and it's on the other side of the sun. So Newton starts thinking, well, is it really another comet? Or has this comet somehow come back again? So this is a diagram that Newton drew to explain the observations of the comet that he'd made. And there it is, observations in November. Then it goes round the back of the sun, reappears in December, and here it is coming up to January 1681 and February, and off it goes.
Newton realizes something astonishing. The comets of 1680 and 1681 are in fact the same comet. One that's followed an elliptical path around the sun. From his observations, Newton makes a bold prediction. Comets, like the planets, must be controlled by the same invisible force, gravity. But it takes another English astronomer, Edmund Halley, to appreciate the significance of Newton's theory. Halley realizes, if Newton's right, maybe other comets have circled the sun and appeared in the sky more than once.
So Halley went one step further. He started collecting historical records of comets that appeared in the past. And what he noticed was that several of them had the same sort of pattern.
In particular, 3 comets seen in 1531, 1607, and 1682. Halley then makes the biggest bet in the history of astronomy. Not only does he suggest they're the same comet, reappearing every 75 years or so, but he boldly predicts the comet will return again in 1758. As the year approaches, the excitement builds.
If I were an astronomer at that time, I would have looked at the sky every night and I would have thought, am I going to be the first person to see this comet?